So I'm super excited today to have speaking to us TTIC's newest assistant professor. So Shiry Ginosar works on various aspects of vision and interaction, but she'll probably tell us much better than I can what she's working on. Joined us just recently, a few months ago, from after a postdoc in UC Berkeley. And this year, at least, she's here some of the time. So, but if you're interested in talking to her, I'm sure she'll be happy to talk to you when you're here, when she's here, or by these crazy digital methods we have. So, Shiry, thanks. I'm looking forward to hearing you talk.
Thank you so much. Thank you, Nancy, for the introduction, and thank you for having me. It's always a pleasure to have some Israeli introduce you because statistically, they're the only people who can say my last name correctly, so thank you for coming today. Okay, so I wanted to talk to you about behavior prediction today, and I have some other things to talk about, but we'll see how far we get to. But let's start with behavior prediction. What I mean by behavior prediction is the ability to observe someone else's actions, be able to predict what they're likely to do, and off the top of that, to be able to actively plan what you should do in response. So this kind of thing is useful in the savannah, but it's also useful in the urban jungle. So this is my one and only ride in a Waymo self-driving car. These things don't exist here yet, so let me tell you, in San Francisco, everywhere you go, there's these self-driving cars now. Some people like them, some people hate them, but they're apparently there to stay. And what these cars need to do in order to survive on the road is be able to predict what every other person in every other car is going to do next at every given moment before they can predict what they should do next. So there are different things to consider when we want to predict behavior. One thing we should think about is what sort of representations would enable this kind of behavior prediction. We should think about what types of information we should care about. And we should think about how we actually make these predictions in practice. Let's start with representations. So there's language, and language models. All these predictive models have been a huge success story. And part of the reason why they're so successful is that language is lucky because they have these really nice tokens. They have discrete words that they can just use as tokens. So a large language transformer takes as input a prefix of words as context, and then it can auto-regressively predict the next word in the sequence. Nice. But do we really need language in order to predict behavior? Both the car and the cheetah didn't need that. And so surely we can predict behavior in video. But what should a visual prediction token be? We can think of a whole spectrum of possible options that lie between low-level and high-level representations. So on the far left, we have pixels, which are the most unstructured, raw kind of bits of visual information that we might use. And on the opposite end of the spectrum, we can think of using objects directly in the 3D world. But before we pick our poison, we have to take into account another set of considerations, which has to do with the fact that imposing more physical object-level priors is going to make our life easier in trying to predict, because we'll have to use less data and less compute. Okay, so why don't we just predict in the cheaper space of 3D models? And indeed, in the case where we have such 3D models, this is a fantastic thing to do. So for humans, we now have 3D parametric morphable models that you can just use off the shelf, and they disentangle the human form into shape, joint rotations, and mesh parameters. And they give you this low-dimensional set of parameters that represents all people in all shapes, in all poses, and you can just predict those parameters, which is cheap and easy, and it's not going to violate physical constraints. And even better, we now have the technology to infer these 3D models of people directly from video. So this is the input video is in the top left, and you just run this model at test time, and you can get a 3D model of the person moving. But we only have good parametric 3D models for humans. To get where we are, people had to train on thousands of 3D body scans. But what about everything else in the world that we can't possibly scan in 3D? So, all right, how about we bite the bullet and we just predict raw pixels? It turns out that's exceedingly hard. Here, there's a couple of different methods, pixel prediction methods, that are in comparison. And once they start predicting, that's when the frames start become yellow. So you can see that the predictions very quickly become very blurry, because the problem is that prediction here is ambiguous. It could be multiple futures. And what this does is that the model averages together all these possible futures into a single blurry prediction. And the problem here is that working with raw pixels doesn't really impose any physical priors. So to learn how real objects behave in the real world, we're going to have to use a lot more data and a lot more compute. So what should one do? Well, what if we go a little bit more structured and take the dynamics of the pixels into account? Let's consider these collections of 2D points. When they're static, they just look like random collections. But when they start moving, the human brain sees 3D motion in these tracks. So tracking through 2D points and predicting in this space might be a good idea. And thankfully, again, we have the technology to do this and to track any 2D key point in video. Now here's an example of one of these methods. There's a couple of them. This one happens to be from DeepMind. But there's no future prediction here. This is just literally tracking points in the video. But then one could use these tracks as training data. So for example, given an image, a single image, we could learn a model that would predict the future dynamics of points on this image. And then, to do a really simple version of video prediction, we could morph the original image according to these dynamics and fill in the holes. And it works-ish. Okay, you know? And what we kind of learn from this is that, as you might have suspected, lots of issues arise when there are occlusions. Because during occlusions, these 2D points will disappear. They don't have enough information about the structure of the object itself in 3D space. All right, so let's go a little bit more structured and agree to pay the price for image patches. Because I know what you've been thinking all this time. You're thinking, I haven't been sleeping this past year. I have seen Sora and it works. They already solved this, right? So how does Sora work and video models like that? In essence, where LLMs have tokens for text that are text, Sora has visual patches. So at a very high level, they compress video into 2D space-time patches and predict in that space. But with all the data and all the compute that OpenAI threw in this problem, it doesn't really work much of the time. Because there's nothing here that is forced to respect physical priors. And learning these priors end-to-end from data, if it's even possible in practice,
it's the multiverse.
It's going to be prohibitively expensive. Okay? So what do I really want? It turns out that what I really want, like a lot of the time, Ken Adelson already wanted in 1994. And back then, Wang and Nettleson described the problem of an object like a hand that's moving independently from the background that is also moving. Okay? And what they were after was a layered video representation that can represent these independent motions. And we're still working on the same problems today, but with very different technology. So what tools do we have now that we didn't have back then? Here's one piece of technology that we have. And that comes from graphics. In graphics, people like Lana and her friends, are working very hard to give us very beautiful 3D reconstruction techniques like NERF for reconstructing a single scene through optimization. So here's the setting. The setting is that you have some object like these drums, and then you have multiple images of the scene from many different viewpoints. And using these different viewpoints, you can estimate the 3D structure of the scene and optimize the resulting 3D shape of the object by projecting back to the 2D image of what it might look like from each one of the cameras. And once you estimate the 3D scene, you can now synthesize an image of it from any given viewpoint. And one of the most recent proposals of how to do this is to use a collection of 3D Gaussians that could be any location, size, color, and opacity. So given an input scene and many images of it from all directions, the optimization might result in this collection of Gaussians, where here I'm only showing their centers. One thing, if you're a vision person, that you notice immediately is that there's something really nice about these Gaussian. And what's nice about them is that they concentrate in areas of higher visual frequency. And those usually correspond to the object in the scene. So here's what they look like if you just plot them together completely opaque. But if you're blending them together with an opacity parameter that you also optimize, we can get a good reconstruction of the original scene. And then we can see how the same scene would look like from any other direction. However, because this is only optimized for this scene, it only works for this particular scene. Okay, so you have to do the same process for every scene you care about. So here's the question. The question is, can we learn from many images to output this 3D Gaussian reconstruction for any image? Okay? So what I'm proposing is to move yet a little bit more towards the structured direction and try to learn a 3D-ish represenation based on Gaussians across scenes. You look very confused. I feel like you want to say something.
I'm a bit confused.
Please.
So when you say that you got it for this image, presumably there is a process that took all those cameras and produced that Gaussian collection, right?
For
You didn't do it manually, right? I mean, you got.
Yeah, but it's an optimization that you do for one scene. And what I mean by optimization is that I'm not learning any weights that I can then go and use in a different scene in any useful way.
But why can't you do this optimization in every scene?
You can't do this optimization. You have to do a test time optimization. You do this at every scene.
So what's wrong with it? I mean, why are you?
No, it's perfect. Rana is totally happy with that. Okay, but I'm not
Why are
happy
you not
because
happy
I'm
with
not
it?
happy because I want to learn something where I don't have to do that at every scene. I want to be able to train on a lot of different images and be able to get an image representation that I could just take an image and then run a feed-forward thing without a whole optimization that's slow and expensive to give me what is the 3D-ish structure of this image.
So you just want to accelerate the runner. Your problem is the runner is not fast enough for you, and you want
There's two things. I don't actually need this accuracy that thing.
Okay.
So they're doing this because, I'm sorry, I'm pointing at you. They're doing this because what they care about is picture perfect 3D.
Sure.
I don't care about that. I just want to see how things kind of move-ish. And I want to do this for
Fast.
video, so I'm never going to be able to do this optimization framework.
Okay, so you want a faster coded version of Fast.
And I want one that I can extract some juice out of, rather than just do it once per scene.
To generalize.
I want to generalize.
But you are okay. That last point I don't understand. When we will continue on, then it'll become your.
And it's like in the Muppets. You know the Muppets. There's the two guys that sit up top. Okay, never mind.
Wait.
Take it as
All right, where was I? So what are we going to do? We're going to try and work with these three Gaussians. Okay, that's what we're doing. All right, so that's what we did. And you can think about the term Gaussian splatting as simply meaning 3D reconstruction with Gaussians. And masked out encoder is basically a technique for learning in a self-supervised way instead of this original optimization setup for a single scene. All right, so how do we learn this representation? Let's start by talking about masked autoencoding, which is a self-supervised image representation learning approach. So given an image, we split it into patches, we mask many of these patches, and we then feed the visible patches into an encoder to get their latent representation. Then we can combine this representation with query tokens for the masked parts of the image, and from this, the decoder's task is to reconstruct the original image. Like any autoencoder, all of this can be trained end-to-end in a self-supervised way using a reconstruction loss. So what we do in our paper is we keep the whole setup, except instead of letting the decoder spit out pixels directly, we're going to ask it to instead predict the parameters of a collection of 3D Gaussians. And then we can render these Gaussians back to the 2D image plane using this differential rendering operation of Gaussian sliding. And we can render it back to the original camera's point of view. So we're just forcing the autoencoder to go through this nice mid-level representation of 3D Gaussians in the middle as kind of a bottleneck. So in representation learning, we often evaluate what we call the image representation, which is the encoded latent from the visible patches. And first of all, I want to assure you that in terms of representation learning, we don't lose anything by doing this. So in all supervised image benchmarks, so classification, detection, segmentation, that sort of stuff, we perform similarly to MAE. And even our training is just as fast as training MAE. Okay, so this is fine, you don't lose anything. But what do we gain? Yes?
So the query tokens in this case correspond to the predefined number of Gaussians? Because there's no longer unmasked patches in MAE that you want to unmask.
And second?
So what are the query? How many query tokens are there? Is that determined by the number of unmasked patches or by the number of Gaussians you want to recover?
For the number of Gaussians you want to recover.
So
Yeah. Yes?
So this is still in 2D space, right? Because
Yes. Very good question.
Wait,
Yes. Yes. Yes?
So you're
Gaussian.
optimizing.
No, the Gaussians are 3D.
Oh, the Gaussians are 3D.
The Gaussians are 3D.
So I
The
think-
image is 2D. We're reconstructing a 2D image with 3D Gaussians.
yeah.
oh,
So if, let's say we were really, really lucky, this is like Nobel Prize lucky, then maybe if you train at many images, you can imagine that you might get different viewpoints of similar things, and then maybe like this, you might have discovered 3D out of this. We weren't, let me give you a teaser, we weren't that lucky. Okay, yes?
I see. But what if you just had in your training data the different viewpoints for at least some of them?
Yes.
Then you don't need to rely on luck.
Yes?
I see.
It's a little more
I know nothing about
I
vision,
don't, we don't, but yes, there's different ways, and I'll mention this again, there's different ways to do this better, which we have not managed to do yet.
I see.
One of them is to say, okay, well, maybe I want a mixed training data. Another one is to, which I really want to do, is to do this on video.
Got it.
Yes.
So usually when they do like Gaussian splatting, they optimize the Gaussian parameters directly. But here, presumably you have a network that's predicting the Gaussians.
Yeah, the decoder is going to.
So you're fine tuning this decoder, or
Oh
you're.
yes.
And how do you deal with the fact that there's a variable number of Gaussians?
There isn't here.
It's just you say like.
Right here, right now, there's a fixed number of Gaussians. Ideally, there would be, and you would do this whole trick where some of them can merge and some of them can disappear. But for now, we didn't do that. We did the simplest setup possible.
So what's optimized here is also the encoder parameters, the decoder parameters and the Gaussians, or just the Gaussians aren't optimized. I guess just the decoder.
I think we just
I don't think
we do the whole thing. Yeah, I think in practice we try it all combination. I think at the end we do the whole thing. Yeah.
Okay.
And it's not optimized; it's trained.
Right.
Yes.
I'm a bit confused about the graph you were drawing was maybe how expensive is it to train on this medium, and then there was information like when you were moving
Like
from
before,
2D
before,
to 3D.
before?
Throughout the talk, right? This like you're introducing 2D patches, then there's 3D
You wanna go
things.
back here?
I'm
Yes.
not sure why 2D Gaussian is 3D Gaussians is here because the information you're really using is still pixels. The raw content you're using is still images. You're just masking
The
some.
presentation.
So
The
the Gaussian,
representation, the Gaussian is gonna be in 3D.
yeah, maybe that. So it's related to Greg's question, maybe. And then you're actually learning as many.
You just decide that you're going to do it with 1,000 Gaussians, and your Gaussians are in 3D,
3D.
and you learn means and covariances of those.
Yeah, and location and opacity. But the question is not how you learn this representation. This graph is for, okay, let's say I had a representation. Okay, let's imagine that I had a 3D Gaussian representation of video or pictures, images, right? Now, what I actually want to do is I want to use this for video synthesis or behavior prediction or whatever prediction you want to do, right? And the reason why this is going a little bit more structured is because once you move to 3D, you have information about motion and pose
Right.
in the 3D
But
space.
except for this red circle, everything else, that's also the information you sense from the real world. Right? Because in the point track, you have a sensor which senses the point tracks. In the 3D objects, you have some 3D camera which is maybe capturing.
I think you always just sense the pixels. But the
Yes.
starting point is just right.
Yes. Yes, pixels. But you might have, okay, most of the time when you do these 3D Gaussians, you actually have multiple cameras that are looking at the scene from all directions. And from multi-view cameras, we can
Yeah.
reconstruct 3D,
Yeah, like
right?
the thing that there might be actually images in the data set of what they use. You are actually using that.
It's still pixels, just a whole bunch of pixels from different
Okay,
views.
okay.
Yeah, okay, okay, yes.
So this is going to be.
That's question
covered
number 2, I heard you
there.
answer it, yes.
So is it? I mean, it goes back to the same question. I'm a bit confused about the 3D versus 2D Gaussians. I assume they're Gaussian 2Ds. Would you ever get? Do you actually get any? Like, why would these Gaussians go out of the slide? Like, why would they be 3-dimensional? If you train it this way, like, what pressures them
They
to?
would if you were very lucky. They don't in practice, they do give you layering. I'll show you in a second. Okay? Yes.
What exactly is a Gaussian? Like, does each Gaussian have a color associated with that?
Each Gaussian has a color.
Like,
Yes,
what
yes.
is it? Oh, okay.
Each Gaussian has a color.
Position,
Yes.
position,
Yes.
or
Not,
covariance,
it's not
opacity.
this color, but it's gonna learn a color. Yeah,
Okay.
yeah, well, yes. Someone else? No? You done? Yes?
What's the loss for decoder
Image reconstruction,
based on
L2
for the original
or L1, either
for the
L1.
original image?
Yeah.
And do you train the encoder or do you use like pre-trained encoders?
No, we train.
You train them as well.
I think so, yeah. Alright, okay, where are we? We were here. Okay, so we don't lose anything. What do we gain? What we gain is in this mid-level representation that we forced onto the autoencoder. And what's interesting about it is that, okay, it doesn't actually learn 3D yet, but it learns some grouping. Because those Gaussians tend to dynamically move and reorganize themselves in a way that focuses on objects, like we saw before. And that correlates with the information density of the image. And what that gives us is that we can learn something about the underlying structure of the natural world, even though we're only observing at test time a single viewpoint of one image. And as a result, we get out of the box figure ground segmentation, we can get a zero-shot layering, and we can get zero-shot edge detection, which are all things that we didn't train for, but just come out of the box, okay? So this is just an initial experimentation kind of direction, but you can already say that there is enough representational power here that it seems like a promising direction. And it might be a good candidate for visual prediction as a token to use. The only open question is, how do we get real 3D here? And I think the answer to that is to make this work in video. And we're working on it, but if you want to volunteer, I'm looking for volunteers. Yes?
Were these experiments done on just with single objects, or were they done on multiple objects? And do you have any comments on centers? Like what sides of segmentations? Was it mostly like towards the center, or was it towards the edge?
A lot of this was done on ImageNet, yeah. Which is single object, which makes it easier to. Yes. But we ran also Koku.
Have you checked or did you notice if the same Gaussian position, because you force the same number of Gaussians for all these different images, so it's possible that the same Gaussian index represents eyeballs or index 5 of the Gaussian.
No, yeah, they don't.
They don't?
No.
Did you try?
Yeah. And also the images are pretty varied.
Yeah.
There isn't, it would be hard to explain all the images if,
Yeah.
Yeah.
But some of them cluster as foreground and background. Is that what the first row is?
Yes. So what happens is that because we let them move in the z direction, they kind of self-organize such that the high frequency ones kind of also separate from the low frequency ones in the z direction. Yes.
Do you need many Gaussians to cover texture though? The spots of this number.
What texture?
The spots.
The spots. I want to say, I don't remember the actual number. I want to say we used on the order of 100 for these experiments. We tried different ones. It's also a question of compute, but yeah.
So is foreground background here actually object foreground versus background, or is it
It's frequency.
due to
It's frequency based.
texture components?
Yeah, it's
So if I
texture.
fit this and add a solid color cat in the foreground of a textured background, to have more constant background.
Yeah, and I'm not saying that we've discovered depth, but we've discovered frequency band. We can. That's how we also do the edge detection, right? We just say, okay, let's go a little bit and then cut, and then we group together the edges to come in higher bands or. Okay. Okay, so that's what I'm going to predict. But what should I perceive? Okay, we're going back. We're done with these Gaussians. We're going back to behavioral prediction, okay? What should I perceive? What channels of information should I care about? Well, this kind of depends on the task, because if I want to look at human social interaction, I might care about lexical semantics or text. I might care about motion. I might care about audio. If it's a speech, I might care about appearance. But I can also think about human interaction at a much higher level. So I might just care about the text labels of the actions, okay? You talk, you're sitting, you're talking on your phone, etc. And then it becomes kind of a text, an NLP problem, okay? If I care about cars, I might want to look at the location or the orientation or the speed or the acceleration of the car. So it kind of depends on what kind of task I'm going to do. All right, but how should we predict anything here? You might think that if we want to do behavior prediction, we could just use physical simulators and be done with it. And here's one example of a really nice simulation of many objects as they interact with each other as they're falling. But unfortunately, behavior prediction is not physics because there's a latent variable here, and that is, what is the other guy trying to do? What's inside their mind? We don't know anything about that. We don't know anything about their goals or intentions. So if physical simulations can't help us, the only way forward is data-driven. And thankfully now there's a real revolution happening now in how we can learn from data. And this revolution is unsupervised. Instead of hand-engineered representation, we're going to use representation learning to learn directly from large amounts of data using large-scale machine learning models. And we're not going to rely on human annotations. Doing this kind of learning on multimodal data is also going to get us to more aligned representations that are more closer to what humans expect about the real world. And of course, we now have compute to do this kind of thing. All right, so we agree on a data route. And now let's just agree that for now we're forgetting about all this token discussion from before, and we're going to assume that we have a discrete agent. This agent might be a person, it might be a car, Might be an object or a hand, but in any case, we know where it is, we can track it. It's just one discrete thing. But how should we do the actual prediction? Like, I took you on this little tour of the world, and now we come to the actual question. One popular option is autoregressive prediction. And if you think about Misty Copeland here, all the context that you need to predict what she's going to do next is what she's done up until this moment. So autoregressive prediction, again, it takes as input a prefix of tokens as context, and at each step it's going to use the previous predictions to predict the next token in the sequence. So all these inputs, they're not ground truth, they're predictions that I predicted before. But what if we want to take into account the other people that we're interacting with? So when you have two agents that are working together, you need to take the other person into account. And this is not really captured by the vanilla autoregressive model. So instead, we're going to propose what I like to call a poly-autoregressive prediction. So instead of one agent, you have multiple ones. You have agent 1 and agent 2 and maybe an agent. And you have some context for these agents. And your task is to predict the future of agent N given its own past and all the other agents' ground truth at this current moment. And then you continue doing this semi-autoregressive thing where these tokens are predicted and these tokens are ground truth. Yes?
So how is this not just autoregressive?
Because it's kind of autoregressive on me, but at any given point, I'm allowed to look at your current ground truth.
You just have partial observation.
I have partial observation, yes.
So it's a hidden Markov model.
Yes.
But why, so the other agents here, presumably they're also reacting to agent N. So
Yes.
they're reacting to what agent N really does and not to agent N's predictions?
Yes.
So what kind of, what are you trying to capture here?
Okay, so this is capturing a situation. Let's say that I have one car and many people. So I'm not gonna, the way it's drawn here, I'm not trying to model all of the agents together. There's another setup that you can say that you're saying, okay, everybody is being predicted, right, at the same time. Yes? And then everybody has to also take as input everybody else's previous prediction.
But you're saying that the people don't actually react to the car. The people would do whatever they do regardless of the car. They ignore the car in their actions.
In this
just
model,
understand
yeah,
what you
in
said.
this model, yes. But if you wanted to model everybody together, then you have to, each of the agents has to take into account the previous predictions of everybody else's.
I guess maybe the point is that if you do observe the behavior of the other agents, that tells you a lot about what their behavior actually is in the future.
Yes.
So it's a little, I guess, cheating in some sense.
It's reactive, right? It's not really.
No, I know, but
Right,
if
I'm not
what
taking
the
your
other
future.
agent did,
I'm
then
not, I don't know what you're going to do. I know what you did until now.
We're just trying to figure out the use.
I'm trying to predict my future step given what you did until now. Which is exactly what I do if I had to dance tango with you. I'd try for you not to step on my toes.
No,
right?
Because he would
Okay,
adjust
I
his
see, I
steps
see, I
based on
see.
you also.
Yes, that's true.
So
But
yes, I'm
but
trying to
it-
understand where in what scenario does this capture?
it doesn't capture this feedback loop to the other agents.
So what does it?
Yes.
Okay.
Okay? This is it's a simplified setup where the other, it's just one dimensional.
So back in the day when you were doing speech recognition and hidden Markov models, you would see the sound wave for a while and your inference about what word was being said. When you predicted the first word, you could look at the whole sequence.
When you're predicting, say again.
When you predict the first token,
Yes.
right, there might be something downstream that if they're reacting to me, say I'm the person agent.
Yep.
And I see what's happening downstream. If I could see what's happening downstream, I mean, you're saying the downstream data is there.
I'm not saying it's there. I'm saying it's no. I'm saying
I
it's
understand your, okay.
Yeah.
Yeah.
it's causal. So I'm not getting to peek into the future here.
All I'm saying is back in the day, we would peek into the future.
Yes, if you peek into the future, of course you can do better, right? But this is really the most simple, like, it's the same as like Shannon wrote this already, okay? This type kind of idea that you can do this. Yes.
Is this a architecture, or are you arbitrarily composing the agent? Because if you have, so how, like, does this mean that the number of agents is fixed at each time, or can you?
Yes, in this setup, the number of agents is fixed at this time.
During training and
No, you can do. I think you can do it so that a test type you could run at a different number. But yes, the number of agents is you can think about it as things. Yeah.
Maybe to help us better, so is it maybe if we insert so these agents,
Yes.
you call them agents, but since they're not actually reacting to anything, maybe it's can we think of them as just as an environment? That you have like side informations about the environment here. The environment is you have a changing environment.
You have a changing environment, sure.
Okay. And so every time you predict your next
A
one.
discretized changing environment.
If I lift something in the environment, then it reacts to me, right?
No, fine, but you can think of how the situation is this gets captures like speech recognition, particularly if you do online speech recognition, right? Your environment is
Yeah, you can think about it as
It's an environment,
discretized items in your environment that are dynamic, right? It's a dynamic environment. Okay. You wanted to say something? No. No. Okay, in practice, you know what? We're gonna skip this because I was doing a little implementation. We can talk about it. Okay, so what kind of things can we do with this? I'm just gonna run you through very, very quick examples without really going into the details. And the main takeaway is that you can model a lot of different problems with this type of thinking. One example is the dancing example. So you have a couple and they're doing their swing dancing. And the goal here is to take one dancer, let's call them Bob as input. Bob is going to be doing what Bob is doing, regardless of what I'm going to do. And what I want to do is I want to predict their partner Alice. So to do this, we went and collected a large data set of couples that are dancing, and we annotate each frame with a 3D reconstruction of the people in the scene. And then what we tokenize is the parametric model of the human body, like we talked about before, but here we're separately tokenizing the orientation, the body pose, and the translation because we can treat them independently of each other. And so if you just do an autoregressive prediction, here the input, the history is in pink, and once we start predicting, it's going to be yellow. If you just look at the lady who's dancing and try to predict her future, it's going to be okay. But of course, once you take into account the other person, you get a little bit of a better prediction. Here's another task. Let's say I just want to think about action prediction in social situations. So this is literally a language task. I'm not looking at the video, I'm just looking at the labels of the actions. And for this, there is a data set already. It's called AVA. It was collected at Google, and there's a lot of videos there, and they're just annotated with action. So here's an autoregressive prediction. It's really hard to see what's going on in these labels, so I'm going to make them bigger for you. But basically, this guy is talking, standing and talking and standing and talking. At some point, the lady starts talking, but the model still predicts that he's hanging and talking, okay, because we're not looking at the lady. But of course, if you look at the lady, then you notice that once she starts talking, which is going to happen, then he actually starts to listening, which makes sense. This is what you want to happen. All right, we can do a similar thing for cars. Here's one of the autonomous vehicle data sets. Here, what do we tokenize? We need to tokenize things about the motion. We look at the velocity, the acceleration, the location, stuff like that. And here's a ground truth. One example. The car we care about, the one we're predicting, is right now is ground truth, but it's going to be the pink one. Okay, so in ground truth, the pink one is standing and stopping, waiting for the other car to go. If you do an autoregressive prediction, where'd you go? There you go. Yes. If you try to predict this autoregressively and only take that car into account, you do what you expect to do, given most of what cars do, which is just drive straight. But if you take the other car into account, then you can predict something more realistic, which is not playing. Why are you not playing? Come on. There. Where you predict the right thing, where you have to stop and wait for the other car to go. All right, you could do something really similar if you think about hands and objects. So here there's a data set. Here there's a data set of hands manipulating objects, and what you have is the pose information for the object and the 3D pose parameters of the hand. And usually what people do with this is pose estimation of the object. So given the RGB of the video, what are the 6 degrees of freedom pose of the object? And what we are going to do is we're going to predict the future pose of the object. We're going to treat the object as one agent that we're predicting, and we're going to treat the hand as the input agent. So what do we tokenize? Here we need to tokenize both the pose of the object and the pose of the hand. And if we predict just autoregressively, we're just going to predict here the rotation of the object. Once we predict it starts being blue, then you can see that that the object rotates completely off of where it should be. But if you take the 3D pose of the hand into account, you can do something much more reasonable. And finally, I guess, I'm going to show you something that you might have seen already if you've been here when I was here last time, which is an example that I did a long time ago where I have a speaker and a listener in video, and given the speaker, I want to predict the listener. And this is exactly the same frame. So here we collected this big data set of video of people talking to each other. What we tokenize are these learned atomic motion elements that we have to quantize using a VQVAE. But at the end, I don't have the single person prediction here, but if you take the speaker into account, you can do something like this. We're given a pair of real videos of listener and speaker.
It really is lovely. I mean, my children are adults. They're being very patient.
You can extract the speaker's audio and facial motion by fitting a 3D morphable model to the face.
My youngest is 18, and my oldest one's like, Peter is, what are you, 45? No, he's a boy.
We predict the motion of the listener.
She's 21. My daughter is 24, right? She's gonna be so mad that I had to guess. She was 20.
And we can also synthesize the video.
24, and we're kind of having to get out of their way. They deserve to not have us on, hovering over them all the time. They're really quite self-actualized.
But the point here is now the inputs are multimodal. So I have from the speaker side, I'm taking both motion and audio. From the listener side, I'm taking the motion. But we're still using the same idea where I predict the listener given their own past, but I always take the ground truth from the speaker side. Yes?
I'm a bit confused about, I guess, all of these. Yes. What is the task you're trying to do here? Because it doesn't seem to me like these autoregressive, what you call autoregressive tasks. Can you clarify what the task is actually?
I'm trying to do a one-directional prediction, so there's not going to be a feedback loop here like there is in.
But how does this connect? But what you're talking about, like in this slide and before, has a feedback loop. So this is exactly what I'm a bit confused.
There is no feedback loop in my prediction. There's a free feedback loop. The real world has a feedback loop. When we are dancing
I know,
tango,
but in your task, there's no feedback loop.
In my task, there is no
but
feedback loop.
But in this slide,
right
if maybe I misunderstood the
Before?
slide, but this slide, for
This
example,
slide, yes.
it looks like there is a feedback loop. Because the striped thing goes from the top into the bottom.
Yes,
That's
but
a feedback loop.
that's a feedback loop that's an autoregressive feedback loop. It's just I can look at my own past. I know what I did in the past. But you don't get to, in this setup.
But you also know the listeners, this is I guess what you just said that the task does not have a feedback loop. So why are you,
So there is a feedback loop. If you're speaking and I'm listening here, what's going to happen is it's if you're one of those guys that just keeps on talking and doesn't change whatever I do,
Hard to imagine.
but whatever I do is not going to affect what you do.
I
Right?
understand.
There's no feedback in that direction.
Sure.
But
But
whatever I predicted I was gonna do in the past, I take that as input for my next time step prediction. So I know what I did in the past and I modify my future based on what I did in the past and on what you're doing in the past. Right?
who's you and me here? Is that where because there's two separate you and me's. You had two different characters there, so that's like you and me. But it seems like the real you and me is the video is the you and these annotations are the me. So I'm a bit confused as to when you say you and me.
The video is the you.
What is it that you're predicting? I think the
Yeah.
wave just went too fast.
Yeah.
I'm sorry. Let's try again.
Let's even go to the speak. Even clearer when you talked about the actions for the different characters. Like all of, like here even. Yeah, let's take this
Okay.
even.
Okay, great. My task here is to predict the future action label of this guy.
Excellent.
So I can do that autoregressively. By just looking at what this guy did so far, it gives me a prior on what they're going to do next. So if they are standing and talking, I'm probably not going to predict that he's sleeping next.
But so you're not using here. So the predictions are not based on the video or anything coming from the video at all.
In this task, I don't look at the video. I'm looking at the action label annotations, and I have them in this data set in 1 Hz. So every second, I know what some person said this guy is doing. So
And what are you trying to predict then?
I'm trying to do what he's going to do next. So for example, you're sitting and you're asking questions. I can safely predict that you're going to continue sitting and asking questions. Actually, if you get up and leave, that would be surprising.
But when you, oh, it's going to happen soon. But when you say what's going
But it won't be surprising.
but when you say when you predict the times 35, you actually know everything he actually did up until time 34,
No,
or
I'm confused.
not?
I know.
Do you understand the structure of the model? It seems very clear. The structure of the
The
model.
structure I understand. I just don't understand how it relates to this problem.
I think
Well, why-
maybe there is a confusion
does it
between
really
training
matter?
and test because there's different things. When you
Yeah,
train, you do
because-
observe the next thing. When you
Yeah,
pre-
because
at test time you predict the entire next.
Models
5
often
minutes.
aren't exactly faithful to the thing you're
no,
modeling.
it's not about faithful. I don't understand the task.
No, okay, okay.
Okay,
So,
Think
so
you
the
did by
task
the
is
Training
that
and
I
test
don't.
disparity and autoregressive models.
The task is that I don't get to in test time. I don't get to see the real thing that really happened. I only get to see my previous predictions. Okay. However, when we train these things, we sometimes
That's
cheat and we use teacher
no,
forcing,
that's
which
fine. I'm
means
talking about just in test time. Okay, so
at test time I don't get to see what this guy doesn't get to see what
Excellent.
he did for real.
And when
Only
you-
what he predicted.
excellent. And then when you add the other character,
When we add the other character, then this guy gets to see what he predicted about himself in the past, and he gets to see what the other lady did for real,
really good. Okay, fine. Good.
but not in the future.
Okay,
only
no,
in the
that's fine.
past.
That's fine. That's fine. Okay. Okay.
But she doesn't get to change what she's doing based on what he did.
Sure,
Okay,
sure, yeah.
because
Okay, that's fine.
I think we're at the question-like session. So does anybody else have questions? Yes.
Sorry, can you go back to that autoencoder architecture? As far as loss.
Autoencoder architecture. Oh, before. You're stuck
My
at
question is
before.
like,
Okay.
how do you construct losses if your loss is like image reconstruction? Image reconstruction?
Here, you're talking about this. Are you doing? Here.
Yes.
Yeah?
Yeah. Where is that arrow from decoder to Gaussian coming from?
Where is the decoder is going to spit out.
Which?
No.
But you
This
construct.
decoder is going to spit out the parameters of the Gaussian. So location in 3D, so X, Y, Z, color, opacity, something else. Color, opacity, location. Huh? Oh, yeah. Yes.
The loss is on the final, like after splatting.
Gaussian is rendered.
The loss is on the image. When you compare this image to this image, there's no loss on the Gaussian.
I mean, maybe there is a rendering procedure which takes
There
the
is a rendering
Gaussians and
procedure.
generates, in
Yes.
a differentiable way, generates pixels.
There is a rendering procedure that's called Gaussian splatting that can take Gaussians,
And that should be
paint the
differentiable.
picture, right? And then you can push the gradients back through that rendering procedure. And that's the magic of 3D Gaussian slatting. That's the magic of like paper zero.
And eventual loss of images is L2 loss between the
L2
pixel
loss.
and the pixel.
On the pixels. Yes. Yes.
So it seems like there's a little bit of mismatch here between the fact that you're using 3D Gaussians to model 2D data.
Yes.
So it seemed like it would be more natural if you had stereo pairs or adjacent frames of a video.
Yes. Yes. So what I really wanted to do is to do this on video, and I still want to do that, and it will happen, where the actual idea was to do this on video and use the fact that there's motion in the video to get multiple viewpoints, right? But given compute constraints and deadline constraints and blah, 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 we first did this single image version, which makes less sense than doing it on video. Yeah.
I'm curious, so in that idea, you would imagine the same set of Gaussians for the scene and they move over time? So you need to impose consistency.
This is streamed. Let's talk about it offline and then we can do it. Okay, yes?
I have a question about the formulation of the poly-autoregressive thing. So I think the other way to look at it is if you extend the state space to be two person at once. Like you just imagine the two person as one state. You extend your state space. Then it essentially becomes autoregressive model where your supervision is only on one of them. So how do you compare them? I guess is there any thing that you want to comment on, like why we cannot look at it the other way around?
I didn't follow. Can you explain that shorter? Yes.
Right now, your state space is a single human or a single object or whatever.
The state space. Oh, you mean the token?
Yeah.
Yeah. Okay.
What if you just extend your state space to be two person at the same time? And then it essentially just becomes an autoregressive model. Now, except that your supervision is on one of the human. Or do you think there is
So you were saying like mush the two people together?
Yeah, that's a single state.
Predict that token.
Yeah.
Yes, but then also
Predict a pair of tokens. Predict a pair of tokens.
Take the pair of tokens and stick them together and then predict. Yeah.
So that's essentially autoregressive. There's no poly there, except for the supervision is only on one of them, right? That's what you do.
Supervision is only on one.
Because you're predicting one of the humans. You can essentially predict two of them actually.
We actually predict two of them.
Right, but then but in this one you only predict on one of them and supervise on them. I just want to know, like, if you do you think there's anything more difficult in training or like better in, like, I don't know, like any way that you prefer this formulation versus the other way to look at it?
So we tried this and it doesn't work as well. And the other thing we tried is if you're a language person, if you're a language person, what you say is well, we do conversations. We just say like Bob said blah blah blah, Alice said blah blah blah, and then we just like concatenate it this way, and then you just do autoregressive prediction where you predict. Show you how you predict. You predict like this. You predict the next agent what do you predict here? You predict the next token, which is going to end up being the different agent at the same time, right? So Bob said blah blah blah, and then Alice said blah blah blah, and you just go like this. But then what you're forcing the model is to learn internally that there's two different things going on here, and each one of them has a different dynamics and different, right? And this is a harder task than to do what we're trying to do, which is to say we want to always predict the same agent at the next time step. Okay? So you're kind of separating between the dynamics of person one and the dynamics of person two. So you're putting a tiny bit more prior into your modeling and you're making the prediction task easier. Yes?
So I think
you're like on first and 5.
That's fine, we'll do one more. So I understand that, I think, I understand, if I understand correctly, and also for the discussion, what's going on here is you're saying that you're comparing just take the tensors, you're comparing predicting what a tensor would do without seeing the other tensor,
Yes.
as opposed to predicting what one tensor would do if you actually get to see what the other tensor is doing. Right.
Yes.
Okay. So the difference here is not so much a difference in model, but a difference of having a lot of really useful additional information.
Yeah, so that's why,
Right?
yes, but we
Okay,
tried to
just
add that information in different ways.
So the baseline, I guess the baseline here, which I think you also did,
Yeah.
is to just look at one frame at a time and compare where the tensor is compared to, just look at the position of one tensor and from that infer the position from the other. That seems like
can you
the
just
obvious
learn?
baseline.
Can you just learn to predict the second tensor from a first tensor from a single
exactly.
frame? That's the
Yeah,
baseline.
that seems like the baseline because that actually uses the same
For
information.
some dancing, certainly you can. For some, you
Yeah.
probably can't.
Or like for the
I
dialogue
didn't
thing,
do that.
where
I
you
did.
can.
I didn't run that thing. I ran the thing where I used the same information and I smushed it in different
Yeah, but
ways.
that seems very difficult, as you said. But it seems that because really you're adding a lot of information here that obviously is extremely useful.
Like in Tango, it probably if you see one tensor, you
Yeah.
probably can figure out where
Yeah.
the second one is.
Or the
Which
dialogue.
is exactly what we're
In a single frame,
doing.
just a single
Or-
frame.
You just translate. You're just doing. Let's say you're saying let's do translation instead of doing future prediction. You're just saying just.
No,
Single
predict
frame
everything,
even
predict
just single
everything.
frame, yeah.
But what's the
Input is post translation and orientation of tensor 1.
yes
Output is post translation orientation of tensor 2 at the
Yeah,
same time.
exactly.
in the same frame?
And that's it.
Okay, but what's the comparison then?
Compare that to what you're doing, which uses the daughter
Oh,
regressive
you're saying
approach.
do I get to
Ignore
see
the history.
Do I get to see the history or not?
Ignore the history.
That's basically.
Yeah, we run that baseline. Yeah.
Okay.
History always helps.
Yeah,
Of course,
but that
yeah.
okay, that seems like the
Yeah,
because
yeah,
then you're
yeah,
actually
yeah,
using
yes,
the same
yes,
information
yes,
to some
yes,
extent,
yes,
as
yes,
opposed to not.
Yes, yes.
Yeah.
In fact, not in one of these papers we have a whole like graph of like how much history do you use and like how much what's the sweet spot? Where is it too much because then your transformer gets yeah. I feel like we're going already on a tangent and we are at the end. So
Or somebody who didn't ask the question yet?
Avram, yes.
To make this, maybe this was the question that was over there, but I couldn't hear it. So, let me ask it again.
That's great.
Right. Okay. So we if we're doing a polyautoregressive with the one dancer, so we have at time t we have the t-1 actual position of dancer 2. We're trying to predict time t of position of dancer 1, given our prediction at time t-1 of dancer 1 and the true position t-1 of dancer 2.
Yes.
Right. Okay. Good.
Yes.
If you imagine running two of these things in parallel, one for each dancer, but using their predictions for the other one, like a multimodal learning sort of, in other words, instead of using the actual position of dancer 2 at time t-1, use the prediction of the other learning algorithm and feed them back and forth. And I would imagine what this might do is at least produce something consistent, even if it's not accurate.
Yeah.
Like they would be spinning around, maybe going in the wrong way, but at least be,
Yeah.
is that
Yeah,
That's
yeah.
right.
The way I would do that though, in practice, is I would still do it all in one model, but I would do what we do actually in training is I would predict everybody at the same time and then just feed it back in, which is still not exactly autoregressive, but that's what I would do. Yes.
What's your thoughts on how to evaluate predictions? Like if you have a car, it turns left, it turns right, like both are correct. There's uncertainty in the future. What's your high level view?
How to evaluate this?
Yes, like there's a ground truth, but the ground truth is a realization of some uncertain random distribution.
Right. So normally what I would do is I would want to see that it's a realistic motion, so it's in the distribution of what I saw in training. I would want to see that it's diverse, so you're not just always parked. So it's as diverse as was the dynamics of the training. And I would want to see that you have a reasonable correlation with the agents that are around you. But for cars, I would also want to see that you're not getting off the road and you're not crashing, right? Which is we're not doing here, but that's
So in practice, do you rely on human annotation, or do you have metrics for each object?
I have not for crashing, I don't, but
Okay.
for the cars, but for everything else, yeah.
So you would see means you will do manual evaluation.
I don't. What did I say that? I didn't say that. No, I don't do manual evaluation.
Okay, but then
I mean, I also do manual evaluation, but that's not. I mean, I do.
is there like a large scale automated like quantitative benchmark, like something like perplexity? You can compare different methods.
Yeah. So what we do is we usually look at some measure of the distribution of the output motion, whatever it is, if it's car or people or whatever. So I look at the distribution of the output motion. I want to see that it's similar to the distribution of the ground truth motion. I look at the distribution of how, let's say you have a pair of interacting agents. I want to look at the interactions between the pair. I look at the distribution of that, and I want to compare that to the ground truth pairs, right? So that was realism, and then that was correlation, and then I look at diversity of motion. So to make sure that it's not just static, or it's not flailing compared to the ground truth. So it's all measures of distributions over dynamics. Basically, so you have a time series, and you want to look at the distribution over.
But you think like there are multiple real values like to performance of the model.
So I have multiple metrics. It's not just one
multiple
metric.
metrics.
Yeah, I have multiple metrics. I don't have a single number.
Yes, you do.